Hello, this is Mr. Gilmore with the 1.4 Geometrical Postulates lesson. Today we'll be looking at a few of our handouts. So one thing I want to make sure you have in front of you before you listen to this is pull out your postulate page that I have handed out to you. There's also a second page that I've given you, which is known as the constructions page. So go ahead and pull those two out. We'll refer to both of those within this lesson. Let's go ahead and jump into our lesson today. First, we define what is a postulate. Well, we have in place many definitions, but definitions, they only exist what they are, right? We don't see any interaction amongst the definitions so far. So what we're going to be seeing then in this lesson is certain assumptions that we make about the objects that we have already established, such as segments, lines, angles, things of this nature. And we're going to see them interacting with each other. For example, um, uh, if we look at the postulate handout page, one of our very first postulates we're going to encounter is what's called the line existence postulate. It's simple. It's one of those obvious things that we should not have to argue to be true. It's just simply it is true based on the obviousness of it. And that is by looking at our first postulate here, line existence postulate. We see between any 2 points, we can create a line. There exists precisely one line between those 2 points. And so because of that, that's pretty obvious, right? If I put 2 points down, I can draw a line between them. That is what we're going to be encountering today in today's lesson. We're also going to see how these postulates lead us into some what we call constructions. So here's our very first postulate, the line existence postulate. It's very simple. Given 2 points, there exists a line through them. It is unique. And it's very obvious, right? If I were to pick any 2 points in our space here, I don't need to give them names, but there they are. I can give them names. Let's call this point A, point B. I can create a line between A and B. Can I create a second line between A and B? Not in Euclidean, right? You're probably wondering, what does he mean by that? What I mean by that is there are other geometries. We'll discuss outside of Euclidean these different geometries. But in our case, it's pretty obvious that if I want to construct a line, I can do it between those 2 points, and it's unique. There's only one line that I can do. I can't create a second line between those 2 points. So that's our line existence postulate. There's a ruler postulate. A ruler postulate, we're going to read this, but I'm actually going to sum it up in 2 very simple phrases. It says that every segment has a length. That's the first one. Every segment has a length. And if I were to give you a line and a length, which of course that length is going to be some sort of number, we may then cut off from that line a segment of equal measure, meaning we can really do 2 things with the ruler postulate. Let's sum these 2 things up in 2 very simple phrases. The first phrase is we can measure with the ruler postulate. We can measure. If I give you a segment, we can measure what that segment is. So we know that that segment has a measure, it has a length. But the second little phrase that this ruler postulate includes is that we are allowed to make measure, meaning I'm allowed to duplicate the measure of segments. We're going to see the ruler postulate come up here in a little bit on our constructions page, particularly involving the midpoint. We can see that we're going to be seeing midpoints. And how do we justify that a segment has a midpoint? We can justify it with the ruler postulate. So here is another one that it involves segments. This is known as the segment addition postulate. What it says is if we're given any segment, let's say our segment is this segment here in our diagram, AB, and there is a point C that lies on that segment between the 2 points A and B, we can then say that the measure of each of those 2 subsegments add up to the whole segment. And that makes sense, right? If I look here, here's AC, right? Here's BC. If I were to add these 2 lengths together, right? Add those together, what's it turn into? It turns into the whole length, AB. That's pretty obvious. That's why we make these postulates, the segment addition postulate. Now, one quick note. It appears that C is the midpoint. Is it? We don't know. It could be. It just means that C lies between somewhere between A and B. It does not have to be the midpoint to be the segment addition postulate. Now let's move on to angles. Let's talk about the protractor postulate. The protractor postulate is very much like the ruler postulate, but this case is in terms of angles. The first one, it says every angle has a measure between 0 and 360. So that means if I were to actually break down this statement into our simple statements that we were talking about earlier, number 1, we can measure. What can we measure? We can measure angles. So if I give you an angle, we know that angle has a measure. We can use the projector postulate to measure it. The second part of the projector postulate says if we're given a ray and a measure between 0 and 360, meaning you have a ray, you have a measure, you can construct a second coterminal ray, meaning it shares the same endpoint, such that the angle produced is the measure of the angle that you desired, meaning we can sum up that into a second statement, we can make measure. So just like the ruler postulate, projector postulate does the same thing. It measures and makes measures of angles instead of segments. Now, following the projector postulate, we have then the angle addition postulate. We split segments up into two subsegments. Now we can split angles into two subangles. What we need, though, is a point to lie on the interior of an angle. So if we're given an angle ABC, so here's our angle ABC, and we're given this point, and we're told that point P here lies on the interior of the angle, great, we have that. We can then construct a ray from the vertex of our given angle through that point P, right? We can have that ray, that we know that ray exists. And then once we have that point on the interior and we have that ray, notice that it cuts our entire angle into two subangles. So we've got the measure of angle ABP and the measure of angle PBC. We can add those two measures together, and it's obvious it will give us the measure of the whole angle, angle ABC. So very much like segment addition postulate works with segments, angle addition postulate is really obvious. We'll see that yes, we can add the two subangles together to equal the whole angle. We're also going to see here in the future one of our very first theorems. I know we haven't talked about theorems yet, or what a proof is, but we're going to see the use of the segment addition postulate and the angle addition postulate used to actually prove many sort of simple theorems, simple proofs to kind of get us into the realm of what proof is. And so, yeah, you'll see we will use segment addition postulate and angle addition postulate quite a bit in the future. All right, before we move on to the last part, let's talk about greater than and less than. Okay, greater than, less than. So let's say you're given a quantity A. Quantity A. I have a second quantity B. Now, I will say that A is greater than B if you were to then take some positive quantity, we'll call that positive quantity P, add it to B, then it will equal the measure of A, or equal the quantity of A. And so this is really when we talk about greater than, we have to establish that there's some sort of relationship between two values already. And those two values are established, one, A, two, B, but then a third quantity such that it's summed to the lesser of the two quantities, which means in this statement we can say that A is greater than B, but at the same time I could say that B is less than A. Now notice that there is a limit on what we can say with this, and it has to be such that P is a positive quantity. It has to be positive in order for us to declare A greater than B. Now, we'll see a quick consequence of less than and greater than on the next screen. Before we move on, though, in plain English, I can just simply say that the greater is the lesser plus a positive, right? The greater is a lesser plus a positive, because in order for us to make up that gap between the greater and the lesser, we need to add something to that lesser to then equal the greater. Now, here's a consequence then of the definition of greater than and less than. The consequence is everything that we're going to be dealing with, length and angle measure, all those things are positive, which means when I am given a segment, I know it has measure, which means it's got to be a positive measure. When I'm given an angle, I know it has measure, which means it's a positive. And so from the segment addition postulate and the angle addition postulate, I then can say that the whole, right, with the whole angle or the whole segment is greater than its constituent subsegments or constituent subangles. This is actually, it's actually a pretty bold statement for me to make this, because really what I'm doing is I'm declaring a statement to be true. There is evidence of this to be true. Yes, it is true. I really should back that evidence up. We're going to see in the next chapter, we're going to prove that these two statements are actually true, proving that the whole is always greater than its constituent parts. So that's something we're going to see in the future. But from now on, it's safe to say, yes, that in segment addition and angle addition postulates, we know that the whole is greater than the part, and we will be able to justify that in the future here. Well, I should say justify it with concrete evidence. All right, now let's move on to the end of our lesson here. We have a couple more postulates. We have the straight angle postulate, which is one that, if you notice, it looks like it has two statements, and it really is two statements. We actually can call this what's called a biconditional, and we may talk about biconditionals in the future, but straight angle postulate says this: all straight angles measure 180 degrees, which means if I hand you a straight angle, here's your straight angle, you can look at that and say, oh, it measures 180 degrees. Bingo. You just used the straight angle postulate. But the straight angle postulate works backward as well. It has a converse, and we'll talk about converses in the next chapter. It means that only straight angles measure 180 degrees. So if I were then to hand you an angle that measures 180 degrees, you can point at it and call it a straight angle. So notice the difference there, that in the first part of our statement, I handed you a straight angle and you called it 180. But in the second part, I handed you a 180-degree angle and you called it straight. That is what's neat about the straight angle postulate, is that it works forward and backward to be true. So yeah, we'll talk about forward and backward. We'll talk about what's called a conditional and a converse in the future. All right. To finish off today, we'll talk about the construction. So you have a construction page. If you look at the construction page, you'll see on the front that you've got a couple constructions laid out. Like the first construction says that through any 2 points you can create a line. Yeah, so we can construct lines. Why is that true? It's because the postulates allow us to construct these. It allows us to make these things true. And so if I give you any 2 points, you can construct a line between them. Right? You can construct even just a segment that connects the 2 points. You'll also see on the construction page that you are allowed to duplicate segment measures. You're allowed to duplicate angle measures. Why? Because we have the ruler and protractor postulate. Yeah, I know that I can measure a segment and duplicate the measure of that segment in another part of my diagram because of the ruler postulate. Same goes for so the same goes for the protractor postulate with angles. And then as you continue down the list, you'll see that we're allowed to construct midpoints. Why are we allowed to construct midpoints? Because we can use the ruler postulate to say we know where the halfway mark is. If every segment has a measure, then we know where the middle of that measure is so that we can place a midpoint. We're going to talk about actually, it's technically a theorem, okay? It's technically a theorem. We'll talk about the proof of that theorem in the future. We'll call that the halfway theorem, so to speak, okay? And we also have that same goes for the angles. With the protractor postulate, we're allowed to bisect angles. So we can construct something called an angle bisector. And we see that in our construction list. Now, as you continue down, you'll see, oh, looks like we're allowed to construct parallel lines. Yes. We're allowed to construct perpendicular lines. Yes. We'll talk about all these different types of constructions in the future. And every single one of these constructions has to boil down to a definition or a postulate, or a combination of definitions and postulates, in which we will turn those into what we call theorems. Now, before we finish this lesson, I just want to make a quick note about this construction page, because here's the catch-22. With constructions, you are allowed to construct only one at a time. You're allowed to use precisely one construction at a time. There's a lot of errors that students make with these constructions. For example, I see a lot of students, they'll do this. They say, let me construct a line between 2 points. Great, you can do that. That is perfectly fine. And then they say, let's call that line an angle bisector. And that is where the error is made. Ooh, no. Yes, you're allowed to construct the line. Yes, you can connect the line between 2 points. But you cannot also declare it an angle bisector. I see that mistake all the time, and we'll talk more about these mistakes that students make in the future. So be careful with the constructions. I like to call these the allowables. These are the allowed things we can do because we have justifications that back them up. We have definitions, we have postulates, and together we can make theorems, and those are allowed then. We are allowed then to make constructions, but be careful. Precisely one construction at a time, and we'll talk more about construction in the future. Now, with that, that is the end of our lesson 1.4. Be good and do good.